Hey folks, welcome to another set of Chemistry 1 video notes. Today we'll be learning the basics of acids and bases. This lesson will cover standards C.8.1, C.8.2, and C.8.3, which ask you to be able to classify solutions as acids or bases and describe their properties, compare and contrast the strength of acids and bases in solutions, and to perform and explain the meaning of some calculations regarding acids and bases. I know you're all excited to get this started, so let's go. Whether you know it or not, you've encountered many acids and bases in your life. Some characteristic properties of acids are that they taste sour, are corrosive to metals, and often found in food. We'll talk more about it later, but the pH scale runs from 0 to 14. Solutions that have a pH value that is less than 7 are acids, and we call them acidic. Bases, on the other hand, often taste bitter, have a slippery feel to them, and are often found in cleaning solutions, like soap. Solutions that have a pH greater than 7 are bases, and we call them alkaline or basic. Water is a really important substance that will come up many times over the course of this lesson. Water by itself is neither an acid or a base, and it has a pH of 7. Before we go too deep into this, please make sure you understand the material from our last set of notes. It might not seem like we used some of that material, like strong or weak electrolytes, but part of my goal was to introduce you to some vocabulary that'll really help you with this lesson. One important thing to remember from that last lesson is the difference between dissolving and dissociating. When a substance dissolves, it simply means that the molecules break apart from each other. Each molecule stays intact as a single unit, but is no longer attached to any other molecules. Dissociation, on the other hand, breaks molecules apart into separate ions, which, if you'll remember, are usually charged single atoms or small groups of atoms with a charge. When a substance dissociates, it produces ions, which is why we can also call it ionization. So with that in mind, let's talk about some definitions of acids and bases. One of the early definitions of acids and bases was the ARRHENIUS model. The ARRHENIUS model defines an acid as a substance that produces an H+ ion in water. For example, if you put hydrogen chloride, otherwise known as hydrochloric acid, in water, it'll dissociate into H+ and Cl-. For bases, the ARRHENIUS model defines them as producing hydroxide ions in water. For example, if you put sodium hydroxide in water, it'll dissociate into the Na+ ion and the OH- ion. One of the most important things you can do as a chemist is to neutralize your acid or base before you dispose of it. I know you've all done the vinegar and baking soda experiment before, and you've probably done some other acid-base reactions, whether you know it or not. One hydrogen ion and one hydroxide ion come together to form a molecule of water. If you remember, water is neutral. Therefore, according to the ARRHENIUS model, if we put the appropriate amounts of acidic and alkaline solutions together, we should end up with a neutral solution of water and some type of ionic compound. The ARRHENIUS model was a fine model that we used for many years to understand the reactions of acids and bases. However, it has some limitations. Picture a hydrogen atom. It has one proton with one electron orbiting around it. If we remove that electron, we're left with the hydrogen ion, or, if you can tell, literally just a proton. The proton has a positive charge and a very small radius, making it extremely reactive. When hydrogen ions exist in water, they tend to latch on to the water molecules, creating what we call the hydronium ion, or H3O+. So when we perform acid and base experiments in water-based solutions, it's more correct to refer to the hydronium ion than it is the hydrogen ion, though we often use them interchangeably because they kind of mean the same thing. More importantly, not all bases start out with a hydroxide ion. That makes the ARRHENIUS model a little faulty. No worries though, a pair of scientists came along and fixed that definition, which brings us to the BRØNSTED-LOWRY theory. Bronsted and Lowry expanded our understanding of acids and bases to focus just on the hydrogen ion, the H+, the hydronium ion, the H3O+, or the proton, if you will. All of those terms are interchangeable, so make sure you understand that as we talk about it. According to the Bronsted-Lowry theory, Acids donate a proton and bases accept a proton. In other words, the substances we consider to be acids have a hydrogen ion that they're willing to give away, and the bases are willing to take on an extra hydrogen ion. So for example, if we put H2SO4, otherwise known as sulfuric acid, in water, it's going to be willing to give up one of its hydrogens and become HSO4 negative. When it gives away one of its hydrogens, the water molecule picks it up and becomes H3O+. In this case, sulfuric acid would act as our acid because it donates a proton. And water would act as our base because it accepts a proton. Another example involves ammonia in water. Ammonia is willing to accept a proton and become the ammonium ion, or NH4+. It's got to get that hydrogen from somewhere, so it pulls it away from the water. Doing so creates the hydroxide ion, or OH negative. In this case, water is our acid because it donates a proton, and ammonia is our base because it accepts a proton. Anytime a substance gives away a proton, another one has to be around to pick it up. As you've seen, water can act as an acid or a base depending on what other substance it's interacting with. When a substance can do this, we call it amphoteric. I'm not going to make you remember that word, but I thought maybe you just wanted a fancy new word to add to your vocabulary. Water is one of the few truly amphoteric substances, and it's vital in acid-base chemistry. I'm not sure if you've noticed, but when I've mentioned acids or bases so far, I've only referred to the reactant side of our equations. That's because acids and bases are our reactants. When an acid loses a proton, it forms on the product side a conjugate base. That conjugate base is the substance that's created after an acid gets rid of its proton. When a base gains a proton, it forms a conjugate acid. The conjugate acid is the new product formed as a result of a substance gaining a proton. So the acids and bases exist on the reactant side, and the conjugate acids and bases exist on the product side. The conjugate base looks very similar to the acid, minus one hydrogen, and the conjugate acid looks very similar to the base, plus one hydrogen. Let's do some examples of that. For our first reaction, HCl gives away a proton. That makes it the acid. Water accepts that proton, making it the base. When HCl, the acid, loses its proton, it forms Cl negative. That would be our conjugate base. When water, our base, accepts the proton, it makes H3O+, the hydronium ion, which is the conjugate acid. For our next example, we have the bicarbonate ion in water. Bicarbonate accepts a proton, making it the base, and the water loses a proton, making it the acid. Hydrogen bicarbonate, otherwise known as carbonic acid, would be our conjugate acid, since it's formed by our base adding a proton to itself. And the hydroxide ion would be our conjugate base, since it was formed by our acid losing a proton. One common misconception, and something I really want you to understand, is that strong does not mean dangerous. It doesn't mean more concentrated. It doesn't mean toxic or bad or anything like that. If you remember back to our definition of strong or weak electrolytes, it simply means that our acid or base completely ionizes or dissociates in water. The more easily an acid or base dissociates, the stronger it is. The strength of acids and bases is a spectrum, ranging from very strong to very weak. To my left here are some common strong acids and bases. For our purposes in Chem 1, I want you to memorize these and understand that any other acid or base is considered weak. So, how do we know if an acid or base is strong or weak? I'm not going to make you run this calculation until Chem 2 probably, but I want you to get the gist of it now so you understand some information coming up in a few slides. So, just listen and absorb. Don't bother writing it down. Many chemical equations run in both directions. Sometimes our reactants stay as reactants and they don't turn into products. Perhaps they don't dissolve all the way, or maybe they don't dissociate all the way, and they just like to stay in their reactant form more than they do their product form. For any chemical reaction, there's something called the equilibrium constant, or KEQ. It's simply a number that helps us to describe the relative amounts of products to reactants that exist when the reaction is at equilibrium. The higher the KEQ, the more the reaction leans to the product side. One type of KEQ is the acid ionization constant. The equation for it says as follows: the concentration of your conjugate base multiplied by the concentration of your hydronium ion divided by the concentration of your acid. The stronger an acid is, or the more it dissociates, the more ions it produces. The more ions that are produced, the more they can react and form your conjugate base and your hydronium ion. So the higher the Ka, the more your acid dissociates. At some point, you may see a table of Ka values. All I really need you to know is that a substance with a Ka greater than 1 is considered a strong acid. The same would apply for bases, except we call it the base ionization constant, or Kb. If you think about it, the stronger an acid is, the more it dissociates and the more it wants to give away its proton. When a strong acid forms its conjugate base by losing its proton, that conjugate base is happy living without that proton, making it a weak base. So if you study this chart a little bit, you might notice a pattern. The stronger the acid is, the weaker its conjugate base, and vice versa. Well, how do we know if a solution is acidic or basic? Easy peasy. If we have more hydronium ions than we do hydroxide ions in our solution, we have an acid. If we have the same amount of hydronium as hydroxide ions, it's neutral. And if we have less hydronium ions than we do hydroxide ions, it's a base. Side note, while we're looking at it, notice the brackets I have around my ions here. Those brackets mean the concentration of. So if I were to read the bottom definition for acids, it would say the concentration of hydronium is greater than the concentration of hydroxide. Here's a handy graph that you might want to copy down to help you remember that. Now, that information from 3 slides ago that I told you was more background information than anything else, here's where it comes up again and is actually important for you. Water doesn't actually exist as just H2O molecules. It swaps hydrogens around like crazy and creates equal amounts of hydronium and hydroxide ions. That means that some water molecules act as a base and some act as an acid. Since that's the case, we can find the Ka of water. If we were to calculate the acid dissociation constant for water, the equation would look like this. I didn't mention this before, but water doesn't have a concentration when it's in a water-based solution. So we're not going to divide by the concentration of the acid, since our acid here is water. Anyway, no matter the situation, whether it's acidic, basic, or neutral, at 25 degrees Celsius, where we'll do our calculations in this class, your Ka for water, which we often just call Kw, is equal to the concentration of your hydronium ions multiplied by the concentration of your hydroxide ions. And that number always equals 1 times 10 to the negative 14. With a little bit of math, in pure water, where the concentration of hydronium and hydroxide must be the same, in order to equal 1 times 10 to the negative 14 when you multiply them, each of them has to be 1 times 10 to the negative 7 molar. Molar because we're talking about concentrations. So put all of that info together. If we have an acidic solution, our hydronium concentration must be greater than 1 times 10 to the negative 7. And our hydroxide concentration must be less than 1 times 10 to the negative 7 molar. The opposite is true for basic solutions. So this is where it becomes important to you. This is your equation that you will use for these calculations. If you know the concentration of your hydronium ion or the concentration of your hydroxide ion, you can easily find the concentration of the other one by plugging it into this equation. You might be saying, well, how the heck do I know the concentration of one of those two values? Easy peasy. In Chem 1, we'll only be working with strong acids and bases. Since the acid or base completely ionizes, you would use your coefficients from your balanced chemical equation to figure out the concentration of your hydronium or hydroxide ions. Usually this is a 1-to-1 ratio. Sometimes it's not. Just pay close attention to that balanced chemical equation. Calculating the concentrations for weak acids and bases is a bit much for Chem 1, so we're not even going to worry about it. For example, if we put a strong base, sodium hydroxide, in water, it'll completely dissociate into sodium ions and hydroxide ions in a 1-to-1-to-1 ratio. In other words, if I have 0.015 molar solution of NaOH, after it dissociates, my concentration of Na ions is 0.015 molar, as well as my concentration of hydroxide ions. So let's do an example. If I had 0.015 molar solution of NaOH, what is my H3O plus concentration? To do this, you must first find the concentration of hydroxide, which we just did. The concentration of our OH would be 0.015 molar. Now that we know that, we can just plug it into our equation. You'll take 1 times 10 to the negative 14 divided by 0.015, and you get 6.67 times 10 to the negative 13 molar. That's your H3O concentration. Chemists really hate big numbers, or very small ones for that matter. And that's the reason we have the concept of the mole, and it's the reason we have pH. pH is a handy number system that helps us understand how acidic or basic our solutions are. It's much easier than looking at those very small numbers like 6.6 times 10 to the negative 13. So, to help with that, we use the pH scale to talk about acids and bases. To calculate the pH, you simply take the negative log of the H3O plus concentration. We already mentioned this before, but in pure water, the pH is 7. The more H3O plus you have, the lower your pH will be, and therefore the more acidic. We sometimes also refer to pOH. This is the same calculation as pH, except we use the hydroxide concentration instead of the hydronium concentration. This one isn't quite as useful in the grand scheme of things, but pH plus pOH always equals 14. So if you can find one, you can find the other, and that might come in handy. For this example, let's keep on keeping on with our original problem. We calculated that the hydronium concentration for a 0.015 molar solution of NaOH is equal to 6.67 times 10 to the negative 13 molar. So what's the pH? All you do is take the negative log of 6.67 times 10 to the negative 13. That gets us a pH of about 12.2. If we wanted to know the pOH, we'd subtract that from 14, or we could do the negative log of 0.015, our hydroxide concentration. We'd get the pOH to be about 1.8. So, is this an acid or a base? Well, the pH is greater than 7, so it's got to be a base. One last calculation you need to know: if you have the pH or the pOH and you want to find the concentration, you simply have to do the reverse of the negative log. Step 1 here has our original equation. In step 2, I flipped the negative to the other side. And in step 3, I did the opposite of log, which is 10 to that. So if I have the pH and I want to find the H3O plus concentration, we simply take 10 to the negative pH. Same goes for pOH and the OH concentration. So for this example, if we know our solution has a pH of 3.4, we take 10 to the negative 3.4 to find that our hydronium ion concentration is 3.98 times 10 to the negative 4 molar. Feel free to take some time to look at this chart. Basically, it shows the different values for hydronium and hydroxide concentrations, as well as pH and pOH values for different solutions. If you study it well enough, you might notice an important pattern that I've mentioned before. Here's a chart that you definitely want to copy down. It sums up all the equations we just talked about. As you start off getting used to these equations, it comes in handy. At some point, with enough practice, I'll expect you to do these equations without this chart. Last but not least, here's a color chart for pH indicators. The pH indicator is simply a substance that changes color based on what pH it's presented with. Different pH indicators have different ranges of pH that they'll change colors to. You'll be able to use these concepts in a lab we do at some point, so just keep this in the back of your mind. Well, I think you've learned enough for this lesson, folks. My apologies for the length of this video. But remember, you can watch it in small chunks and take breaks in between. Or watch it all at once, then rewatch bits of it later. Use this as a resource to familiarize yourself with this material. It's a lot to take in, but I know you can do it. As always, if you need any help, please let me know.